Hello, I'm Louis Imershein, a Principal Product Manager at Red Hat. With me, I've got Kevin Klein, a Principal Program Manager at SentryOne, a well-known Microsoft data MVP and author of SQL in a nutshell. I've also got Sanjay Rao, who's a Principal Software Engineer on the performance team at Red Hat. Before we get started here, I want to remind everyone to explore everything PASS has to offer. There are free resources online at pass.org. And I also want to remind everyone to evaluate our session. If you submit this evaluation before Friday, November 20th at 5 p.m., you can win fabulous prizes. So for our agenda today, we're going to do a brief overview of SQL Server on Linux. Just a few quick reminders. We'll discuss where to look for trouble. That'll be a great little session from Kevin. We'll talk about the dark art of Linux performance. And then Sanjay will give you an intro to Linux performance monitoring, and he'll talk about the ins and outs of Linux tuning. So how do we get here? Well, the big secret to SQL Server on Linux is that it's done through an abstraction layer. And that abstraction layer itself sits below another abstraction layer called the SQL OS. So most operations are boiling down to the same platform assembly code, regardless of where they're running, whether it's Linux or Windows. But performance critical code calls into Linux directly. So there's a very small amount of assembler via direct APIs that sets up the stack correctly and processes the results. The end result of this is that it's the same SQL Server, whether you're running it on Windows or you're running it on Linux. The differences are at the operating system level, but there are some Linux-only SQL Server features. Of course, there are containers supported on Windows for SQL Server, but production containers are only supported on Linux. And those are supported in Docker, in Cryo, which is the container engine for OpenShift, and in Podman, which is a container engine for Red Hat Enterprise Linux and a lot of other modern Linuxes. So all of those are supported. Another thing is Enlighten mode for Intel Optane persistent memory. And this can have a big performance impact. Here's an example from HP. You can see column store performance on cold queries. And you'll notice the number on the left is an NVMe drive from HP. And the number on the right is persistent memory being used in Enlighten mode. So this can be a big deal to give you performance, particularly if you're running SQL Server Standard Edition and using column store. So at this point, I'm going to turn things over to Kevin, and we will take a look at where to look for trouble. Kevin?
Okay, everyone, so let's dive in. And the first thing I want to point out is that I actually have a methodology that I use to do troubleshooting on SQL Server. And so we're going to spend just a moment or two going through that to make sure you understand that there's kind of a methodical approach you can use for performance tuning and troubleshooting for root cause analysis. The number 0 on that list, they're not, a positive number yet, because 0 is your shortcuts. And if we live in the land of best practices, which not all of us get to, what we'll do is we will monitor our SQL Server systems normally as part of our regular routine. And as part of that routine of monitoring, we will construct some kind of benchmarks, if you will. Because if you don't know what normal is, how can you truly know what abnormal performance is? So you need to know what is normal for most of the commonly used performance metrics related to CPU, I/O, memory usage, and so forth. So that's one thing that is a very important kind of shortcut. The second shortcut you can use in any sort of troubleshooting or performance tuning methodology is to ensure that you know what your system looks like when it's stable. Because depending on your environment and the balance of power between developers and administrators, it's very possible that people might go out and change things without telling you about it. So, for example, one of the things I did in the early days was I just took a hash value of all of the objects in my databases that I had to track, and then I would just do a daily check on that value of the hash. And if it ever changed, I knew someone had changed something in my database. It takes a little setup beforehand, so we don't all get to do that. But if you do want to incorporate that into your daily life, send me an email or a note, or check out one of the references I'll make a allusion to later, so that you can get those scripts yourself. The other thing you always need to start with is to also check your error logs. And you need to know if the error is inside or outside of SQL Server. So in the Windows world, for example, one of the things I found out the hard way, without looking at the error logs, I'd waste a lot of time thinking that, oh, I know what the problem is in SQL. Let me go start working on some code that was just recently rolled out. And it turns out the real problem was a bunch of DNS errors, and the DNS server was giving me a problem. So check your error logs. Those things will be revealed there. So it's at step 2 and 3 that we're going to focus our time for the next couple minutes. And we're going to go quickly because the session really isn't about SQL Server tuning and troubleshooting as much as it is all of the things you can do with Linux, right, for this purpose. So the first thing you need to do when you are diving in on getting to the root cause of a problem, or generally trying to improve your performance, is you need to know what your weight statistics are. And if this is a new concept to you, it's an extremely important one. So we'll spend some time on that and kind of explain how it works inside of SQL Server. And then what you do is, once you have the broad weight statistic or statistics, because it could be several together that give you a kind of a top-down view on how your SQL Server is performing, then you need to go an extra step and use some of these other resources that we have here, DMVs, Perfmon counters, extended events. And you need to use those to correlate the exact problem back to the weight stats. The reason for that is there's frequently what we call a knee-jerk response, and then there's the true, well-researched response to a troubleshooting or performance tuning situation. And so if you don't do that correlation step, I've seen many people who spent a lot of time and in fact fixed the wrong problem. So let's look at these in a little bit more detail, and then we'll have a bit of a demo as well. So again, these first two are outside of the scope, but we'll start with number 2 and then go to number 3 here on our checklist. So to understand the SQL Server weight stacks concept is to also understand how SQL Server maintains threads. And that is done by a process called the SQL OS. Now, a long time ago, SQL Server ran on only one OS, and that was Windows. And so at that time, they very closely coupled the SQL Server thread management with the Windows thread management system. That has been abstracted away a little bit, but the concepts all still apply. The analogy I actually like to use, instead of CPUs, think about you're sitting in a car waiting in line to at your favorite fast food place, for example. And that would represent every CPU, every core in the CPU available to you. So here I've got a little image and I'm saying scheduler CPU 1. But if SQL Server has a dozen CPUs available to it, it'll use as many as you allow it to have access to. And, so you're idling in line, you're asking for something from the little kiosk where you can place your order at the fast food place. In the same way, we do that here with SQL Server. We ask it something along the lines of, show me all the salespeople in the Northeast region for this year who have met quota, right? We're asking for something. And in order to get that query answered, SQL Server has to line up all kinds of resources. It has to get locks on all the records you need. It has to have CPU processing power. Perhaps if the I/O system is really slow, then it might spend time waiting for the I/O system to respond. So in fact, what happens is SQL Server has 2 queues for each scheduler, for each CPU. We have them divided into kind of general names here. So we have the suspended queue. So what SQL Server says is, okay, you've asked for all these salespeople in this and such region that have met quota. I need those locks. I need the data itself. It's not loaded up in a cache. So that means I have to read the data off of the files and load it up into cache. That will provoke a wait. We have to wait for that to happen. And that is called page IO latch, and that SH there means shared. So that's literally the time spent waiting to get a shared access, not an exclusive access to those records for the read process that you just asked it for. In the same way, when you're in line at McDonald's or some other fast food place, and in my case, I have 7 kids. So in the old days, when we were all in one minivan, if we said we need X number of French fries, they'd say, pull up and wait, because they didn't have enough for us at the time. Same thing here. We don't have what you want, so you get suspended just for a moment, microseconds, milliseconds. And SQL Server then says, you know what, there's all these other processes out there that are simply waiting on a chance to get some access to the CPU. That's called a signal wait, because those different SPIDs, system process IDs, have kind of given the signal to SQL Server, said, hey, coach, put me in, I'm ready to play. All I need is CPU. Whereas the others in the suspended queue, those are all waiting on specific resources. And the time spent waiting is tallied up and put into general buckets that help you understand what the problem is. Those are called your resource waits. Okay. And as I mentioned, if the resource that you need becomes available, you get to move off of the suspended queue and over to the runnable queue. Okay. And you become a runnable process. And as soon, kind of in a first in, first out process, as soon as someone moves off of one of the CPUs and then moves probably into the suspended resource wait kind of queue, someone else gets to move up from the runnable queue and moved up directly onto a CPU so its work gets done. That's how it works. So now let's go a little bit further with that. Let's talk about the most common wait stats. And again, don't have a lot of time to go into this, but what you will find if you look at the past session schedule, that there will be deep dive sessions on each of these areas, okay? So there'll be one for wait stats. There'll probably be one for, if not several, for extended events, dynamic management views, and Perfmon counters, right? So this right here is to just really give you a flavor of what sort of issues you might experience and what these different wait statistics reveal to you. For example, if we find that one of our wait stats that's up at the top of the list is SOS scheduler yield, we know just from the previous slide that SOS means the SQL OS. And so scheduler yield means you have a little bit of time sitting on the scheduler to find the answer to your question. And now it wants you to step off because you're making people wait. And so that scheduler yield means that SQL Server is moving many different threads in and out of the schedulers, trying to find one it can do more work on. In the same way, you can tell that you've generally got memory problems by some of the memory counters that I've got called out there for you. Page latch, underscore, and it could be that lowercase x could be shared or an exclusive. So anywhere you see that underscore x, you know that I'm talking about shared for read and exclusive for write operations like insert, update, and delete. And again, I'll show you in a demo in just a sec. The same kind of thing applies over on dynamic management views. Just to give you a flavor, a little taste, a little sample, there are dynamic management views that can tell you everything about what's happening inside a SQL Server. The thing you need to keep in mind here with the dynamic management views is that there are both overarching sort of DMVs that can tell you generally information about how the entire system is performing, such as the different wait stats counters that I have there, as well as the performance counters. But you also get enormous value at a very low level, granular level. So these kind of queries can help you get precisely to the smoking gun, if you will, for your performance issues. We'll dive into that momentarily. And then finally, one of the last of my slides here is on the Perfmon side and the X event side. Oh, and by the way, one thing that is fantastic about the SQL community, unlike some of the other communities I've been a part of, it's very open to sharing. So if you don't want to write or reinvent the wheel, It's all out there for you. There's somebody who's probably written this code already and locked it down, and it's excellent performance, and it's ready for you to take advantage of. So one example is Glenn Berry. He's called Dr. DMV because he does so many of these kind of neat queries around dynamic management views. And then finally, I also want to point out the Perfmon counters and extended events, which I'll show again in the demo. There's a number of them that are really important. Actually, I once wrote a big poster that had 72 on it that were really important and a kind of good rule of thumb for you to use for each of those. If you haven't already established a baseline or a benchmark and know what normal is for your system, and you'll see a little bit of that code in here. The thing is, though, if you see the term performance counters and you have some experience, you recognize that relates to Perfmon, which is a Windows tool for managing not just SQL Server counters of metrics indicating performance, but also Windows. And so you cannot use Perfmon, the performance monitor tool, in Linux. So I'll show you a little bit about how you can get close to that using a simple query. All right, so let's jump over to a demo now. So here we are in Management Studio. And one first example of how you can find out what is going on with your weight statistics is to use the Dmos weighting tasks. This is useful to find out exactly what is happening right now at this moment. And it tells us all the weight statistics relevant information at a SPID level. So if I execute this right now, we'll see all the different SPIDs that are consuming and rolling up, aggregating different weight statistics of different kinds. Notice, however, though, that any SPID that's 50 or less typically is going to be a system SPID, a system process ID. So maybe different processes used to manage and just organically keep Service Broker alive, as an example. So I don't use this one a lot, but it is very useful for finding out what query at the moment, what user or job is consuming a lot of resources, for example. So anything over 50 typically is going to be your users, but it's very transient. It represents what's happening right here and now. The one I use most commonly is one written by my friend Paul Randall at SQL Skills, and there's a link for it. And notice that it's going to be quite a large query. And it also says to exclude quite a lot of these different types of weight stats. That's because all of these weight stats that he has listed here are those that are used to kind of naturally and organically keep SQL Server alive. So I've had people, come up to me at conferences and they're like, I've got this terrible XE dispatcher weight that's really, really big. It's like, that's okay. That's kind of like your blood pressure. We don't want that to stop. It's normal. So he excludes all of those. The latest version of this links into his very, very useful library of weight statistics. So if you go to this URL up here, it'll take you to it. And so for each of these weight statistics, he has a link that tells you exactly what each of these do. It's really cool. So it's a CTE, and we can see, how he has done some different calculations to, make the multi-decimal point into percentage numbers here. And so when we query this one on my system, since it's just a demo, I might have one or two weight stats. Let's see. Okay, yes, because I'm not doing much work. We see that I just have the XDP preemptive weight task. And notice it divides out the specific resource weights and signal weights. One very quick and easy rule of thumb is that if your resource weights are low, but your signal weights are high, that means CPU pressure. You don't have to look at anything else. You have too much happening on your CPUs, okay? So again, the idea here is to know what ballpark we are in. Then we will use the correlating information we get from DMVs, from Perfmon, and extended events to precisely zero in. So just to move quickly on a few Dmv type queries. For example, if the different weight statistics showed us that we had IO related issues. So we saw that we had a lot of asynchronous IO weights, and we also had page IO latch weights. we could drill in on that and find out, well, which of the databases is it? And so here's a DMV that uses IO virtual file stats, and it tells me the IO in megabytes and the percentage for each of our different databases. So TempDB makes sense. It's usually one of our most busy databases. It's top of the list. But then I have my benchmarking databases for TCP-C and TCP-H. They're quite high as well. I'm not going to go through every one of these, but there's lots of good queries here in this set of queries. This is one that shows us latency per database file. And this can be quite useful to determine how slow or fast my IO subsystems are. And that uses the DMIO virtual file stats and the DMV that keeps track of the files of all of our databases, sys.master files. And then I'm going to actually skip ahead of here a little bit to show you one of my favorite queries written by Jimmy May. And what this one does is it looks at all the queries that are happening in the database, gives us lots of information about, say, the execution count. How many times has it been run since this SQL Server was restarted? And it calculates all kinds of, it keeps track of all the different writes and CPU and all kinds of things. And then it enables you to actually sort by what is important to you. So if you want to know who's doing the most writing, then you could sort by total logical writes. I'll go ahead and execute this one just so you can get a taste of what it will show us. It gives you the text, database name, database ID. If we move over here, we'll see when it was created, last time, how many times it's been executed, so that we can kind of perceive if we have one of those death by 1,000 cuts scenario. You know, one small query that's not very big, but it's executed 60,000 times since the last time you polled it 3 minutes ago. Reads and writes, the amount of worker time, which is basically CPU, how many physical reads it has, and so forth. So there's a lot of great information in here that you can simply sort by what it is the wait stat has told you is consuming the most resources. That's one way to do it. Another way to do it might be to zero in on Perfmon. Perfmon also gives us some different capabilities too. For example, it can point out to a specific sort of red flag situations, like how many times we have deadlocks happening. That's not really pointed out specifically in a wait statistic. Also, in the old days, in order to clear out your different Perfmon counter values and your wait statistics, you had to restart SQL Server, and that was pretty terrible. If you ever need to zero out those values while you are actually running SQL Server, you don't want to restart it, there's now a DBCC command to do that, DBCC SQL Perf with the clear parameter, and you can clear those out. If you've never used it before, the dynamic management view, SysDMOS performance counters is the same as using Perfmon in Windows, except that it doesn't have access to the actual OS level weights performance information. So when we execute this, we'll see the instance in SQL Server that I have here, the different kinds of counter objects and the instance of the object. So we can see them all just by querying that particular value. We can also do a little bit of math. For example, if we wanted to look at, say, buffer cache hit ratios, or if we wanted to look at something like page life expectancy, which is another kind of well-known value from Perfmon. Let's see here. Let me go forward a little bit and show you a little procedure as well for calculating and keeping track of these values too. So here's a little stored procedure, Perfmon for SQL Server, MS SQL. I'm going to go ahead and grab all of this text. I have to scroll a long way down here. But this is kind of based on the poster I told you about that I'd written. And so you could probably see when we are going all the way down through, you might have seen a reference to, oh, I don't know, IO, for example. That's what this is about. It collects all this information. You could store it in a table long term if you have no other means of seeing it. But what it does is it tells you all 72 of those important Perfmon counters, say buffer manager, and the current value that it's pulling out. And if you don't, here's the actual value, that is. And if you don't know what a good value is under other circumstances, it'll tell you. So for example, memory grants pending, that was one of the values I had on the slide, top 10 from the field. If this is greater than 0, this tells you you have memory pressure. Again, it's one of those kind of quick and easy. If you see that happening, then you know you have memory pressure. So that's one of the interesting things you'll see. When you look at the when you look at the weight stats, you might see that there is a, say, a IO performance indicator in the weight stats. But when you come and look at Perfmon and you see that you have memory grants pending and it's 72, really high, that's when you know the knee-jerk response that, oh, I had IO issues according to the weight stats. That makes you think, oh, maybe my disks are slow, something like that. But then you come and check against these other correlated metrics and you say, memory grants pending is 72. Well, what you really have is that you probably don't have enough memory. And so SQL Server is constantly having to go back to the disk and load things up as soon as memory happens to flush out a little bit of space for you. And so you want to go to the second level of analysis to make sure you know exactly and precisely is what is happening. Then you could go to the Dmv query I showed you to tell you what the top specific SPIDs and SQL statements were to see which of those were consuming the most memory. And maybe you've got a developer who's written one of those horrible queries that select star from a really big table with a poorly written where clause, right? So that's the Perfmon stuff. And then finally, there's also extended events, which are wonderful. And kind of what I would say is the best way to go nowadays in recent releases of SQL Server. And so here's just a very simple example. So what I'm going to do is just, first of all, see what I have running right now in terms of extended events. And you can also come over here to management and extended events and see what sessions are running. In fact, let me refresh that because the demo is actually showing up on that list. So now I'm going to create a new extended event, and they can be very, very targeted. You should spend a little time getting to know the different extended events that you can choose from. In this case, what I'm going to look at is to see what the query optimizer has chosen as the cardinality estimator. There's a couple different cardinality estimators available in SQL Server after 2014, and you can actually turn those on or off for backward compatibility. For Linux, then you could enable the old cardinality estimator if you wanted to maybe migrate from a SQL 2012 over to Linux on Red Hat. So now I've enabled that, and if I turn that on, I can look at it over here under sessions. If I refresh, there it is. I can also just directly query the DMV. And then when I run queries, what I'll see is the different values here. Let's go ahead and say, watch the live data. So nothing at the moment. We'll come back. Oh, and there I have some queries happening from other processes in my system. And I'll just run this one here as well. And so we get our results back. And now we can check over in the live data and we can look for that specific query and see what cardinality estimator it used. So you can do some really cool things with the extended events there. So I'm going to go ahead and stop that and drop the session. The key thing to remember is that you start with weight statistics that put you into the kind of the general ballpark of what your problem is likely to be. But you can't stop there because some of the weight statistics are really only valuable in knowing some related weight statistics as well. For example, CMIM threads and then the thread pool or SOS scheduler yields and memory related. So you want to know several weight stats together, and then you go the next level deeper, verify and correlate against the other bits of performance information, the other performance metrics. And that will kind of bring you full circle back to the specific query or queries that are causing those weight stats to aggregate.
Well, that was awesome, Kevin. That's really great information. And now we're going to talk about the dark art of SQL Server on Linux. And really, the main point I want to make is that it's not magic. It's just different. You have different performance monitoring tools. There's no Perfmon on Linux, of course. Different ways to tune the system. Some different hardware support, like I talked about some of the Optane memory enablement that's only available for SQL on Linux. Different ways to use hardware. Different ways to integrate with Active Directory, with high availability, etc. When it comes to monitoring tools, there are a lot of them to choose from. One of the things that Linux loves is choice. Some of the most popular ones are Top, which gives you a dynamic view of the processes in a running system. So this displays a whole bunch of information, including a system summary at the top, and then a list of tasks currently being managed by the Linux kernel. And you can actually, with various commands, choose to sort that information in different ways. You also sometimes just need to get a picture of a specific point in time, and you can do that with PS, which is a different utility, but provides similar information. There's also Vmstat, which I think Sanjay will use later. That provides instant reports of your system's processes, memory, paging, block input, output, interrupts, and CPU activity. And you have those that view over a selected period of time. So it's kind of a little bit different kind of report than Top. And then there's SAR, which is really about daily reporting. That's a classic utility that came over to Linux from the Unix world. And there are modern tools. And when it comes to modern tools, the two that are most exciting are the Bcc Tools package, which lets you figure out what's actually going on in the kernel and see what's going wrong. Okay, and this is based on the extended Berkeley packet filter. So it's essentially taking advantage of virtualization technology to run analysis inside the kernel with minimal overhead. So you're getting very much up to the microsecond information and correlating that information to help you figure out what's broken. And the second set of tools is PCP. There is one PCP command, but there's actually a suite of tools, services, and libraries built around PCP. And these include tools for monitoring, visualizing, storing, and analyzing system-level performance measurements. Really quickly, I'm going to take a look at some of these measurements using Grafana, which is a web-based tool. We'll go ahead now and we'll log into Grafana. Here, I've got this already set up. And we'll take a look at some of the dashboards that I've created here. The vector host dashboard is basically real-time PCP statistics. And you can see those statistics are being collected now. So we have the percentage of CPU, the load average, memory utilization, disk utilization, CPU that's busy, so for users and for the system. And there's just a whole lot of other information here, context switches, whether processes are runnable, a run queue, which you'll see here is a heat diagram, a bunch of information about memory, network, and down here I think we've also got some storage information. A lot of network stuff. There's disk latency, IOPS, throughput, and disk utilization. And a really nice heat graph, again, for using BCC to look at disk latency. Let's also take a look at some SQL statistics, because PCP also supports a PMDA for obtaining SQL Server statistics. And so this dashboard, so we just started collecting this, it includes some system performance information, but then it actually dives down and takes a look at some useful SQL Server statistics. For example, user connections, the SQL Server Memory Manager. It looks at batch requests, network I/O states, access methods, statistics compilations, and the plan cache. So, you don't have to go and hit everything from the command line. All of this can be turned into dashboards that are easy to understand. I definitely recommend that people everyone take a look at PCP as a tool set. There's a tremendous set of tools there. And one of the great things about them is that they're all being managed by a common framework. So all the statistics that are being collected can be managed, logged, tracked. It really is a great way to go. So that's PCP and quick look into the Bcc tools. With that, I'm going to go ahead and turn things over to Sanjay.
Thank you, Louis. So my name is Sanjay, as Louis mentioned, and I'm part of the performance team, and we do performance engineering on Linux. So I'm going to talk a little bit about what are the main tools that we use and how do we approach performance tuning from a Linux side. So next slide, please. So one of the key developments that happened in the last few years was because, like Louis said, Linux is about choice. And so when you come out of with a default installation of Linux, it's like a Swiss Army knife. You can pretty much run any type of workload on it. But then, with a Swiss Army knife, you need to know exactly which tool to pull out of that Swiss Army knife handle to effectively use it, right? So likewise, it kind of became a little challenging for some of our customers Linux customers to fine tune their applications. So a few years back, there was a framework called Tunedy that was developed, which allows you to dynamically apply certain performance tuning settings, whether they're kernel settings or other optimization stuff, which can be applied as sysctl values. And they can be applied by means of this Tunedy profiles. So once you apply a profile, all those settings are dynamically applied, and you can immediately start seeing effects of that on your application or on your system. One of the good things about Tunedy is it can be rolled back, and you can also create your own custom profile. So here you can see when you go on a system and you type Tunedy profile list, Tunedy-admin space list, you will see the profiles that are available to you by default. With Microsoft, they've been developing their own Tunedy package. And as you can see here, I mentioned a slight note, a small note there, which says that it is actually packaged separately. So it's not available with your Linux installation base, but you can actually apply it through means of a package installer. So in this TPCC-based workload, which is an OLTP workload, we took it and we took a default profile of throughput performance, and we ran the application, and we were slightly under 2 million transactions per minute, as you can see from the chart there. And by applying the SQL profile, we were able to get about 7 to 8% improvement in performance. So you can see that just by saying Tunedy admin profile MS SQL, we were able to improve the performance. So it's a very easy way to apply certain settings in order to get that improvement.
Good point here, Sanjay, is that typically if you are in the cloud, you may find that we're using the guest profile, and the difference between the guest profile and the MS SQL profile is even higher. So we will often get calls from customers who have not realized to run the Tunedy profile. They're still using one that's optimized for a virtual guest. And the difference there is huge.
That is absolutely right, Louis. Thank you for pointing that out. But the advantage is, as soon as you find that out, you can simply apply the profile right away, and you can start seeing the performance gains. So we'll take a look at that SQL profile that we just saw, the profile that gave us that improvement. So in the next slide, you can see, so the way the Tunedy is designed is it's a hierarchical framework. So throughput performance was the default profile that was running on the box when you started out. And the SQL profile, the settings, and as you can see, it's not a lot, but it is certain things that are instrumental in improving the performance of SQL. So you'll see right there in that slide, in the SQL box there, the top line says include throughput performance. So what they're telling you is we are using the throughput performance profile as our base, and you'll see all the settings for throughput performance in the box above, and then making some changes that are instrumental in giving you those performance improvements while you're running SQL Server. So we saw what happens when you can just take a profile that's uniquely designed to benefit your application and improve the performance. But if you're running on a large system, for example, these days most of the systems are they're all NUMA based in order to allow the systems to scale, because we are seeing terabytes and petabytes of memory. And the best way to access those kinds of memory is to have separate memory banks in each of the sockets. So this little diagram here talks about how a typical system would look like if you put it out on a sheet of paper. And you can see I've got 4 sockets here, which we represented as nodes. And you have all the different cores within each socket, and they individually access memory banks from within these sockets. Now, what happens is if you're running a system which has a whole bunch of applications running on it, including your SQL Server database, your backups, and something else that's running your application, there is a good chance that they'll start competing for resources, or when the memory gets laid out, things might end up on different NUMA nodes, and you might actually see an impact of that on your performance. So the way you can do that, improve your performance on the Linux system, is to do some NUMA optimization. So how do you do that? So there are a whole bunch of commands that will let you do NUMA tuning. There is actually a graphical tool called Tuna, which is available on Linux. One of the easiest way to do it, especially if you're using the command line approach to run some of your other tools or applications on Linux, is to use NumaCTL. So in this, there are several options in it. And if there are a lot of Windows users who are now looking at implementing SQL Server on Linux, your friend on Linux is man pages. So any command that you need to read up on and you need more information, you simply type man and the command name, and it'll give you the manual pages for all those for the commands and all its different options. So here there are several examples listed. So you'll see that we use NumaCTL and various flags to control the memory and the CPU resources. And what you can do is you run NumaCTL, you use the different flags for the resource control, and then you run your workload. So if you want to start up your SQL Server database, and you know that it can be accommodated within a single NUMA node, and that's all you need, you just simply include NumaCTL before your startup command and tell it on which nodes you want to place your SQL Server. And likewise, you can do that for your other applications, and so you don't have them competing for resources. So this one actually shows you how you can benefit from it. So you'll see here that the unaligned, when we run some virtual machines, which is shown by that when you look at the PEDs, and it tells you that it's a QEMU KVM, which is a Linux virtual machine. You'll see when they're unaligned, your resources are coming out of different NUMA nodes. But once you align them, you can see how they're all cleanly aligned within each NUMA node. And this has almost a 15 to 20% improvement in performance. So you are seeing that they are not competing for resources, and each one is making sure that they have full access to a socket and its resources, including the L2 and L3 cache, which can have a really nice impact on performance. The other implementation on Linux is using huge pages. Microsoft has made this very simple. So there are other databases that run on Linux platform, if you're familiar. They use something called a System 5 shared memory. And those kind of memory implementations actually require huge pages in order to take advantage of reducing the number of TLB misses. But with kernel version 3 onwards, we implemented something called as transparent huge pages, where the regular pages are coalesced into huge pages transparently behind the scene. And Microsoft SQL Server actually takes advantage of it. So you can actually set it up. And this example here shows that it's actually a small application called memory, which shows you that it just allocates pages and it dirties them. And in this, when we enable the transparent huge pages, you can see that we actually get almost a 2x speed up.
Now, Sanjay, isn't this actually also done automatically in the TuneD profile?
That is correct. So what they're doing is in the TuneD profile, in case this has not been enabled, they enable the transparent huge pages in the Microsoft SQL Server profile. Yes. Great. So this example shows you again when the transparent huge pages were not implemented so the red bar is without the huge pages, and then when we implemented the huge pages, we again saw about 5 to 6% improvement in performance. So the other thing you can do on a large system is in Linux, one of the ways works is memory is allocated and it's never deallocated as such. As new processes come along, they request memory, and if there is no memory available in free list, then it will go through your LRUs and start flushing pages out. if you run an application that does your backup and it uses up all of your page cache, and now once the backup is complete and you want to free up that page cache so that new processes that come in will have candidates waiting for them in the free list, you can actually do that by flushing page caches. So I've actually listed the commands. You can go ahead and run them. And by dropping those caches, whether it's freeing up your page cache pages or slap cache pages, or both page cache and slap cache. So this will only flush pages that have already been. Even if you use this, we call it a big hammer, but it will make sure that the information is written out to disk if the information in the caches are still dirty. So you don't have to worry about dropping some. The terminology we use is drop, but it's really not dropping it. It's making sure it's flushed and it's freeing and adding those pages into your free lists.
Well, you anticipated my question there. It's like, ooh, what about dirty pages? But you got it.
Okay, this one is very important. So again, this I think is kind of a known tuning methodology when it comes to databases, and it's very effective when it comes to Linux, because when you are filling up your page cache and you need to flush your data out into your file system, Kevin just talked about memory pressure and vis-a-vis the inability or the effect of a slower disk system, and how things can kind of get muddled. And so one of the things we've done is, in order to provide scalability in the newest Linux kernel, they have a per file system, per device flush daemon. So a very easy way to tune your database is to make sure your data is distributed across multiple file systems on Linux, multiple devices, which is kind of a no-brainer. But in many situations, what happens is people, especially with large shared storage systems, people tend to use a single device, and that is where sometimes you can run into scalability issues. So I actually captured some data, which we'll see in the next slide, where we saw some really nice gains by making sure our file systems were spread across multiple file systems. So in this case, we already started slightly about 2 million transactions per minute. And by just distributing my files properly across multiple file systems, I was able to get another 10% improvement in performance. Some of these things seem like a no-brainer, but over a period of time, as your data continues to grow, and you'll find that you added more data files and spread out your database. But from time to time, it's useful to use some of the queries that Kevin shared and look at some of the Linux tools to see if you're hitting one disk consistently, because your data distribution is kind of got skewed. And if you make sure that that data gets redistributed or rebalanced, you can actually get some really good performance gains out of it. So there are some reclaim ratios. Earlier on, I talked about flushing the data. So the way things work in Linux is there is a dirty background ratio and a dirty ratio. So as your pages get dirty, I've used the blue line in the bottom there, which says, if you set your dirty background ratio to 10%, we'll use that as an example here, and my dirty ratio is set to 20. As my pages get dirty, till it reaches this 10%, it does nothing. It's dirtying the pages and your system continues to work. But once it reaches this 10% threshold, a backup flush D wakes up, a daemon that flushes your dirty blocks, wakes up and starts flushing things in the background. If you have a particularly aggressive application that's dirtying blocks at a very high rate, you'll start seeing that it'll keep going up till it reaches this dirty ratio setting, which is on this system set to 20%. When it hits that, in order to maintain system integrity and to make sure that the data is not lost, it actually stops processing to write data out to your disk. So in many Linux systems where people run multiple applications, they complain that I'm running an application and all of a sudden I see my system just pause. So this is actually what's going on. So and especially on large systems where if you think that, I have a lot of memory, let me just allocate and run things in my memory and not worry about flushing. You have to worry about flushing, because one, if your system goes down, there is a good chance you'll lose a lot of data, and which will have to be recovered using all kinds of recovery mechanisms built into the database as such. But still, it's a time-consuming process. So one of the ways to take care of this is to tune this and lower your dirty background ratio and on large systems. So make sure that your background processes are woken up early and they flush data sooner. And in certain cases, if you've got very strong redundancy architecture like RAID and other implementations, you can actually increase your dirty ratio slightly higher so that most of your activity is being done in the background. Swappiness is another setting. Kevin, do you have a question?
If I could just interject, that's quite a bit different than on Windows, because with Windows, when you have any dirty page, even if it's just 2 or 3 bytes on the page, the next time the checkpoint comes along, it's going to try to clear out those pages, even if they have next to nothing. So that's a pretty significant difference. I'm glad you taught me that.
Right. So like I said, with Linux, obviously it was designed on smaller systems, and today we are scaling into much larger architectures. This is by design that cost of I/O is higher than accessing memory, so they kept things around till you feel a real need to push things out. But on a very active system, tuning is required to make sure that you don't hit up against these thresholds and things start backing up and systems go into these pause modes. So and that can be really bad for performance. Swappiness is another thing that helps you define how aggressively you want to swap. And by default, the setting is 60%. So what happens is, if you want to aggressively reclaim page cache memory and put it into free list, you can decrease this. Or if you want to get more aggressive in keeping things in memory, if you know that you have a fixed memory set and you want to keep things in memory, then you increase it. But one of the risks with that is, unless you're absolutely sure, if you hit beyond the certain limit of memory, then you'll start swapping things out, which is not good. So this is by default, the setting is 60. Most of the times you don't need to touch it. But for database applications where things are very aggressive and you want to do reclaim at a higher rate, then we recommend reducing this. Don't increase it. So these are some of the Microsoft recommended trace flags that we implemented on Linux. This was done with the help of the Microsoft performance team. So I've shared some of the commonly used trace flags. It can also have a very big, drastic impact on performance. So as you can see here, there are several trace flags. One of them is 834. Once you set them, it actually uses the transparent latch pages for the buffer pool. If it's not set, it won't use it. And then there is one more for the FUA capable storage. This is only applicable for storage subsystems that support it. So there are several trace flags that can be used to improve performance. I've listed a few of them. It needs to be explored based on the type of workload one is running. So you can see here, it was a nice big jump. We were still around 101.5, slightly over 1.5 million, close to 1.6 million when we started. Then we applied the trace flag and it brought us very close to that 2 million. And then you saw the other tuning data that I showed earlier, which took us well up to 2.1 million, 2.2 million TPM. So you can see the progressive, as you apply certain tuning mechanisms or methodologies, you see that how you go from gains to gain. So where we started 1.6 to 2.2, that's almost like 25 to 30% gain in performance, right? So that's something
free performance.
Exactly. It's all only those changes brought us to those levels. So
very nice.
Yeah.
Now I guess it goes without saying, but since some of our audience might be novices, don't apply those trace flags on a Windows-based system.
That is true. These were specifically correct. Very good point, Kevin. So these were specifically, put together by the Microsoft SQL Server Linux team, working with us and doing extensive testing. They came up with these list of trace flags, and I mean, some of these performance tuning things should not be applied willy-nilly, but obviously the huge page one can be applied. And then if it's an FUA-based storage architecture, then you apply that one. And some of these you can apply and you can see the impact right away. Vmstat is one of our favorite tools here because, you can just get a glance at the system very quickly if things are not working. I talked about how the system can get into these modes where you start seeing pauses. So I have these two comparisons here between Vmstat running on traditional storage versus running on solid state devices. So it's the exact same workload. And if you see the top ones, and the green portion shows you the IO stuff, the yellow portion shows you the blocks in, blocks out, so the actual read write, and the pink portion shows you if the system's swapping. So that's something that you look at right away. If you ever do a Vmstat to get a quick system glance. And if you're swapping, then you know things are not right. The other thing I wanted to quickly highlight is if you look at the second column from the right, you'll see the weight statistics listed above. And because I was having IO weights, my system was actually idle because it was spending time sitting around and spinning for IO completion. So you see a lot of idle time. The exact same workload when we went to solid state, the weights were all gone, and you can see the user time is 90+%, and system time, and system is no longer idle or very little idle time. And the performance went from, because I was able to do these IO completions much quicker on solid state, from 150 megabytes per second, it went to 500 megabytes per second throughput on a solid state device. And my system was actually more than doubled its performance. So this is actually hardware tuning, not necessarily anything to do with Linux. But I used Vmstat to kind of illustrate that, how you can use it to like a window into your system and see how things are behaving. And I just wanted to talk about a little bit about the collaboration that we've had with SQL Server for a while now. As you can see here, I've used RHEL as a point, but basically when we were transitioned from kernel version to from version 3 to version 4, as well as from SQL Server 17 to 19, this chart clearly shows us that all the gains we got as we work closely with the SQL Server team. So SQL Server, the engineering is very, very serious. They have a very, very strong Linux team. And I think as we evolve from version to version, both on the Linux side as well as on the SQL Server side, we are seeing some tremendous gains made in terms of performance. Another small utility that I wanted to share, it's to look at your network performance. But you can see here, this was an example of running a DSS workload, running it with different frame sizes, so 1500 MTU versus 9000. And you can see that when you're running to network-based storage, by using a larger frame size, I was actually able to quadruple my performance. It was sending out bigger TCP packets because it has a bigger frame size. So again, this was to kind of use SAR to show all the different network devices we had on the system and the kind of information it shows you. So if you want to look at if your network's having issues and you want to quickly see how many packets it's sending and receiving, and if it's not hitting those network transmit rates, you can just run quickly SAR and just at a quick glance say, okay, why am I not hitting the rates that network line promises? So like Kevin said earlier on, you should have a good understanding of what your baseline performance is going to be in terms of hardware. If you need to know if you're hitting those, because you need to know if you're hitting those rates or not, right? I mean, having the unrealistic view of your system can make you think, oh, I might get by tuning, I'll be able to get to the next level. So that's not necessarily true. So kind of wanted to point out that obvious thing. So here's a few more performance monitoring tools that Linux offers. So one of my favorite ones is Perf. It's a good tool to kind of capture a snapshot of your system. It's not behaving properly, and share it with your support team to kind of explore what kind of performance issue you'll be running into. This one actually talks about the various ways you can run it. You can dynamically run perf top in order to see what's going on in your system. Or there is a way to actually record and report. So you can actually record the perf information into a file and then send it off to your Linux team to kind of look at it and replay it back and look at what's going on in the system. Or you can run specific commands. So we've used this on occasion to gather statistics of a particular workload. So you can analyze the behavior of the workload from a kernel standpoint. So this is a quick view of the perf record and report. So I actually ran perf record while I was running the SQL Server workload, the OLTP workload, and then I ran the report to see what was going on. So you can see clearly that it shows the SQL Server, the different pairs, the CPU utilization. It's a little bit of an eye chart, but if you had a bigger screen, you can actually look at the different routines and what it's invoking from a Linux standpoint. And it shows you all the different, the locks, lock routines and things that are being called by SQL Server. So if you start seeing some of these lock routines drift way up to the top, that might actually start giving you some ideas about contention that's happening in your database.
All right, thanks, Sanjay. And I want to thank you too, Kevin. There are more resources that you can use that I think you'll find helpful. There are performance best practices from Microsoft and configuration guidelines for SQL Server on Linux. There is a demo of how to automatically tune SQL Server on Linux using built-in facilities of SQL Server. From Red Hat, there's a great blog on optimizing performance with Microsoft SQL Server 2019 on RHEL 8. There is other materials here as well. There's a blog on Performance Copilot and a excellent monitoring and managing system status and performance section in the documentation from Red Hat for Red Hat Enterprise Linux. Also from SUSE, there is a system analysis and tuning guide. With that, I want to thank you, and I especially want to thank Sanjay and Kevin for their participation today.
Thank you. Appreciate it.
Have a great day.